sequence of subspaces. We have this first subspace is a one-dimensional subspace. This and it lives inside a two-dimensional subspace here, which is this yellow plane, and then it lives inside R3. So flags have types, which essentially are the dimensions of the nested sequence of subspaces. So this would be a flag of type 1, 2, living in R3. So we kind of store the type, or some people call it a signature, in this format. So obviously, when I sort of defined a flag, I said this just has to be a nested sequence of subspaces of a vector space. So the dimensions can be different. So we'll talk about that in a moment. But for notation, what I use here is I use a tall, skinny matrix with orthonormal columns whose basis vectors span the biggest subspace here, this yellow plane. And so this is a representative where the first column of this matrix is a vector that spans the first subspace, and the next two columns, and both columns span this second biggest subspace. And so we say that this is a flag, and to denote kind of the nested, to assign this nested structure to the columns, with notation, we have these like double brackets. So we say this is a point on actually the flag manifold of type 1, 2 living in R3. And the flag manifold is essentially the set of all of these flags of the same type. So this is sort of the space of all these nested subspaces with the same structure. So this is our first example of a flag. So maybe to just reiterate this in a little bit more generality, so you can have K subspaces that are all nested, living in Rn. And you have this type, which is the dimensions of the nested subspaces in increasing order. And it lives in Rn. So I assign n1 would be the dimension of subspace 1, V1, n2 would be the dimension of subspace 2, V2. And the flag manifold is the collection of all flags with the same type. And sometimes it can be annoying to write all of this. So we're just using n+1 as kind of a placeholder. In other works, people use obviously other notation, but this is what I like to use. Okay, so what the heck do we do with flags? So flags, in fact, can arise in averaging subspaces. In fact, when you average subspaces with respect to a certain distance, it outputs a flag of a certain type. Flags also, you can also actually just average flags using a distance between flags. And you can also use flags to represent hierarchical data sets, where sort of you embed the hierarchy into the flag structure. And also principal component analysis kind of naturally outputs, in fact, the flag of principal directions. And we've done some work to produce robust flags of principal directions and play around with all these different variants of sort of principal component analysis and subspace recovery type algorithms. So first off, let's talk about subspace averages. So here, the red and the blue plane would be two-dimensional subspaces of R3. And if you were to compute their average, maybe you'd get something like this purple plane, and it would live between the other two planes. So that's the idea of a subspace average. So let's just recall averages in Euclidean space really quick before we start talking about a subspace and flag averages. So, I mean, if you have a data set with some inliers, which are blue, and some outliers which are orange, you can compute the mean of your data set and the median of the data set. And the mean will be somehow more corrupted by the outliers than the median. So the median will more be representative of your inliers, whereas the mean is more pulled toward the outliers. So we say the median is more robust to outliers than the mean. So if we have like a data set in Rn, um, and we have, a distance, here we just take the 2 norm between the vectors. We can compute the mean and the median as solutions to optimization problems. So the mean is the point y, which is closest to all other points in the data set with respect to Euclidean distance. So you take this mean and you measure the distance to each one of the points, and you do the square of those distances. And if you take the minimizer of that, that gives you the mean. And I mean, we know the solution to this problem is just adding up all these points and dividing by how many there are. The median, on the other hand, the only difference between these two optimization problems is that the median no longer uses this square, which somehow turns this into more of like an L1 norm optimization problem, and in fact ends up generating something that's more robust to outliers. However, with this median problem, there's no, it's not as easy as just adding up the points and dividing by how many there are. To find the median, you have to use these iterative algorithms, and one of them is this iteratively reweighted least squares algorithm, which can also be called the Weisfeld algorithm. That essentially, to find the median, you compute iterative means and reweight them at every step. So those are sort of the mean and the median. The mean is less robust to outliers. The median is more robust. Mean is easy to compute. Median is harder to compute, and you do it by computing iterative means. That's one way to do it. So those are averages in Euclidean space, but we want to work on the manifold of subspaces. So I've put some names up here, the Stiefel and Grassmann manifolds, but we'll talk about them individually. So first off, I'm introducing the Stiefel manifold because I'll use it later, and I think it's also like kind of essential to parameterize the Grassmannian manifold as well, or the Grassmann manifold as well. So the Stiefel manifold N is the set of all nk frames in Rn. And before we think about any of this flag stuff, let's just see how we represent a point. If we take a point in this space, it's represented by a tall matrix with orthogonal columns. And so sort of these are basis vectors for a subspace of dimension nk. But yeah, so that's kind of what this is. And you can write this as a quotient of groups as well, but we're going to leave it like this. And in fact, this space is, I think this equals maybe, not exactly equals, but is, what would I say? Similar to, I don't know exactly what goes in this equal sign. It's, yeah, I'm not sure exactly what it is. I don't want to misspeak. But you can think of this as a flag of this type. A flag of type 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 nk living in n. So sort of you increase the subspace dimension by 1 at each step. And forgive me for putting this equal sign in here. I'm going to say that these two spaces are similar, and I think that exact similarity I'd have to look up to see exactly what it is. So the Grassmann manifold, why did I introduce the Stiefel manifold? Well, we're going to use it to parameterize subspaces because, right, we have the Grassmann manifold is the set of all nk dimensional subspaces of Rn, which again, this isn't exactly an equal sign, but you can think of it as FLNK semicolon n. And in fact, yeah, I have to know exactly if this is an equal sign. But anyways, what you do is you take a point on the Stiefel manifold and you look at its column space, and that gives you a subspace, right? So here we're Stiefel manifold, we talk about frames, Grassmann, we talk about subspaces. Okay, so let's look at an example. So an example, if we have GR12, which is one-dimensional subspaces in R2, this is essentially just lines through the origin in R2, and you have your representative unit vectors, which live on the unit circle. represented by these green lines. And now let's talk about how we measure distances between these subspaces. The most natural distance here is just the angle between them, which is this orange theta. And it's called the principal angle between these two subspaces. And it's also, in fact, the geodesic distance on the Grassmann manifold. But it can be kind of hard to compute. And so people generally use, or people also use this chordal distance, which is the sine of the principal angle, which can be computed as the Frobenius norm of the difference between the projection matrices. Here I'm just using the 2 norm because we're working in GR12. But with higher dimensional subspaces, you have more principal angles, and this linear algebraic way to compute the sine of theta, to compute the chordal distance still holds. So in general, this generalizes to a chordal distance between points on GR, NK, N. Okay, so now we're ready to talk about chordal distance subspace averages, or subspace averages with the chordal distance. So if we have a data set, which is a set of subspaces, like we saw in the first slide, think like a bunch of planes through the origin. And we have our distance, which is this chordal distance. Then we can compute means, which is adding up all the distances squared. So find the point that's closest to all the other points using the distance squared. This is like, looks like I'm copying and pasting what I did in Euclidean space, right? And you can find the median. And you do the same sort of thing. You remove the square. Now you have these optimization problems. And in fact, when we, with the algorithms that we use to solve these, we output flags of this specific type. And so we say that these mean and median kind of average subspaces into flags. And forgive me, I have a little typo here. This should be a mu. Okay, so how do we compute these things in practice? I just want to provide like a little outline of how this works. So we take our original problems and then we simplify them for the mean and the median into these problems with orthogonality constraints. The one on the left is essentially solved by any rotation of the eigenvectors of P. I'm not going to say how you compute P, but P comes from these X's. And then with the other one, you can simplify it, but you can't get rid of the pesky square root in the distance. And so then you have these two algorithms. The first one can be solved by an eigenvalue decomposition or singular value decomposition. And the second one can be solved by iteratively reweighted SVDs. And this algorithm is very similar, I think, to some stuff that has been done in the past. Like these iteratively reweighted SVD type algorithms have been around for a bit. So this flag structure, when I say it's a flag, it comes from the order of the singular values in the SVD, where sort of you order these nested subspace dimensions based on the singular values. Okay, so now let's use these for something rather than just talk about them abstractly. So we're going to work with this data set where we have a collection of little video clips. And we want to cluster these video clips and see how good the clustering is with respect to the labels. This is called the UFC YouTube data set. I'm just going to work with a subset of it, actually. So we have some videos, and the way we translate a video to a subspace is we vectorize and stack each frame. We compute the SVD of the matrix, and then we look at the first few left singular vectors. So kind of what we're looking at is the span of the columns of this vectorized matrix. So sort of the span of the video over time. And so this representation can be useful in the sense that it's somehow a little bit more robust to illuminations and things like that. So if you had a light that was flickering in the video, using a subspace representation for the video would sort of mod out for that flickering light. So anyways, here's a small result that we had. So the idea is we're going to do clustering. We're using chordal distance to compute distance between these subspaces. Then we use averaging to run the clustering. And we get something that looks like this, at least with this data set. I was just comparing the chordal, the median of subspaces to the mean of subspaces, and the median gives you slightly higher cluster purities. We had another experiment with different data sets where we compared to other subspace averaging methods as well, including the canonical mean on the Grassmannian. Okay, so now we're moving into averaging flags. So a flag is a sequence of nested subspaces of Rn, right? So here we're working in R3. We have two flags. We have the blue one and the red one. Blue one is a line, a blue line living inside a blue plane, and the red one is a red line living inside a red plane. I ended up using the same picture as before, but this is just to visualize it. And then this would be the mean of these flags, this purple line and plane, and then the line lives in between the blue and the red lines, and the purple plane lives between the blue and the red planes. So now what we have to do in order to compute flag averages is we have to come up with a distance and then find a way to solve this optimization problem. So first off, there's a chordal distance between flags. So now we have two of these flags. And I hate to do this, but we have to think about how we represent flags, right? So what we're doing is, I don't think I wrote this down again, but the way we represent a flag is by a matrix, a matrix with orthonormal columns. So this is kind of a point on the Stiefel manifold. And what we do is we separate this matrix into blocks, where each of the blocks somehow encodes each one of these nested sequences of subspaces. And yeah. And so the way we measure chordal distance is what we do is we measure between flags is we measure the chordal distance between these blocks on the Grassmannian. So that's kind of the idea. And then we add up all these chordal distances. So if we have X, it breaks down into these blocks according to the flag structure. You have Y, which breaks down into these blocks according to the flag structure. Now you measure the chordal distance between each one of these blocks on the Grassmannian, and that gives you the chordal distance between flags. So this is what it ends up being. So you kind of take the sum of the two norms of the sines of principal angles. And actually, wow, my apologies here. This is not quite what it is. It's slightly different than this. So yeah, my apologies if there was a way for me to erase this part. But the intuition is here. This is kind of what it is. Forgive me, but these two formulas are slightly off. It's the square root of the sum of the squares of this thing and the square root of the sum of the squares of this thing. So not quite. Okay, so now let's talk about chordal distance flag averages. So we've defined the chordal distance at least intuitively, and I made a small typo in defining it mathematically. But the idea is you have a set of flags, and now we want to compute their average. And we have our mean, which is the minimizer of the sum of the squares, and we have our median, which is the minimizer of just adding up all the distances. And so essentially the chordal GR, what happens here is that the mean on the Grassmann manifold and the median on the Grassmann manifold averages subspaces and outputs a flag, and the mean and the median on the flag manifold averages flags and outputs a flag. So we have some algorithms here. So we had this original distance problem, and we can simplify it to a problem over the Stiefel manifold again, like we did before. Again, I'm not going to explain how these P's come out, but this is now kind of a problem over the Stiefel manifold. And then we solve the left problem with Riemannian trust regions on the Stiefel manifold using this package called PyManopt, which I did not develop, I'm just using. And then you sort of do iteratively reweighted chordal flag means to compute this the chordal flag median. And we use these to average motions. So it turns out that there's a way you can represent like motions in Euclidean space. So these are rigid motions that involve rotations and translations. We call it SC3 is what we'll call the group. There's a map from this that takes you to oriented flags. I'm not going to talk about what an oriented flag is, but there's a map from SE3 to take you to flags, and there's a map back to SE3, and we can translate our flag averaging algorithm to work over this space. And that's what we did. So we took data in SE3, translated it to this flag, computed these means and medians, and translated them back. And it turns out that with some synthetic data, when we compare our method to standard methods, this red and this blue line, we get lower errors with recovering the true average of these synthetic data. Cool. So now I wanted to mention hierarchical data sets. So I think so far we've kind of talked about subspace representation for data, but we haven't really talked about flag representation for data other than this specific problem of representing motions. But there's kind of this general question is maybe there's a way to use flags to represent other types of data. And so maybe with hierarchical data, we can use a flag to represent hierarchical data in some way that sort of preserves essential information. And so, right, so far what we were doing for subspaces and even for flags as well, I did some experiments with videos, is you kind of take the video, you vectorize and stack the video, you run an SVD or a QR decomposition, and then you just take the output of that to represent the data. But now our goal is to use flags to represent data sets with other feature hierarchies, or with specifically to represent data with feature hierarchies. So for example, maybe you'd have a pixel hierarchy in an image. So you have some sort of, all the pixels that represent trees live inside all the pixels that represent forests, which live inside all the pixels which represent the entire image. Or you could have like a spectral hierarchy where you have like maybe a hyperspectral image and you have low frequency bands living inside low and high frequency bands. Another idea for this pixel hierarchy that I've played around with, hasn't been that useful, is looking at like sort of an expanding radius around a central pixel, which is kind of fun. And this is kind of the idea. The title of this slide is flag rep. It's this idea that we had to solve this problem. It seems to work okay. We'll be presenting at an ECCV workshop with a poster on this, but I think in most experiments that I've been playing around with, it hasn't done anything super good. So, but the idea is you take a data matrix with n samples and p features, and you have some sort of nested hierarchy for the features. So you have this first set of features is inside the second set, is inside the third set, all the way up to the k. And then kind of what you want to do is you want to encode this hierarchy in the subspaces of the flag representation, where you have a flag that's like, has a nested feature hierarchy. So the correspondence would be like A1 would correspond to the first subspace, and you get a dimension out. A2 would be the second subspace, you get a different dimension, all the way up to AK. This is kind of a cool problem where you're trying to get subspaces to represent this feature hierarchy. Just wanted to mention the problem. We have one algorithm which kind of works, but it'd be cool if there was something that worked better. So I also wanted to talk about principal directions, and specifically how flags play a role here with principal directions and principal component analysis. So let's start by talking about principal directions of a data set. So if you have a set of points, like these black dots, you can compute these things you call the principal directions of the data set, which would be these unit vectors u1 and u2. And in fact, if you do this with, a data set in higher dimensional Euclidean space, we're working now in Euclidean space, you can order the principal directions based on the amount of variance that they explain. Like the first principal direction is the direction which contains the most amount of variance. The second contains the second most amount of variance, and so on. So there's sort of this natural ordering of these directions. And in fact, each of these directions span a subspace, which is represented by these lines. So we've got an ordered sequence of subspaces. What are we thinking? We're thinking flags. And we will get there, but there are a lot of different versions of these principal component analysis or different methods to sort of recover a subspace from data. And you have ones that are robust to outliers. You have ones that instead of recovering a subspace which contains your inliers, you have a subspace that contains the outliers and some correspondence between these different things. And it's quite a big world out there, with many different algorithms. But I want to talk about it from a flag perspective. So yeah, these principal directions are actually used for dimensionality reduction and for outlier detection, things like that. Okay, so flags. Now we're talking about flags. So PCA or principal directions are naturally structured on a flag of this type, which is kind of equivalent to the Stiefel manifold, right? Where you have less variance on one side, more variance on the other. And this is the sequence of nested subspaces. You take the subspace with the most variance with one principal direction. You take the subspace with the two-dimensional subspace with the most variance, which would be the subspace spanned by the first and second direction, all the way up. So this would be this one-dimensional subspace with the most variance, the two-dimensional subspace with the most variance, and so on and so forth. And this forms a flag, right? And the flag type, since the dimensions increase by one each time, is exactly this type here. And so sort of the visual with our previous example, as if we have the first principal direction being this blue line, the second principal direction being this gray line, and your data being these black points. You can look at this blue line, which is the span of U1, living inside the span of U1 and U2, which would be this orange plane, or yellowish orangish plane, living inside this reddish orangish R3. So this would be a flag of type 1, 2, 3. Okay, so flags are kind of already in PCA, right? And people have thought about this before, and other people even started optimizing over a flag manifold to find other flags of principal directions. And in fact, work came out just recently that is called the curse of isotropy. Let's see, it's called the curse of isotropy. I'm not remembering the end of it, but it essentially kind of tells you the type of flag that comes out from running principal component analysis, like exactly if there's maybe a different type of flag rather than just this simple one, using this sort of formulation, probabilistic PCA formulation. It's really interesting. I'd be happy to share the link later. But anyways, I didn't think of that. I was thinking more about robust principal directions. So what are these? If you take a mean-centered data matrix and you run PCA, we're doing like what we did before, right? This is one way to formulate PCA here is an optimization problem. We remove the square and we get a robust version of PCA that's somehow more robust to outliers. And so the principal directions are the columns of the minimizer of these problems. And this is really the intuition that we want to see, is that if you have a data set and you have some outliers, maybe the first robust principal direction will be less corrupted by the outliers, meaning it'll better capture the inlier data. Whereas the purple, the normal principal direction is kind of corrupted by these outliers. This is also just a toy figure, but gets the idea across. So there are a lot of different ways to formulate robust principal directions, just in terms of formulating these optimization problems. But what we want to do is we want to kind of what we're calling like flagify these optimization problems, like the actual objective functions. So we start with an algorithm like principal component analysis, which looks like this. This is one way to formulate principal component analysis. And we can think about it as an optimization problem looking for a flag where we say just optimize over a flag. And then what we can do is we can make this robust by removing this square. And then what we can also do is embed the flag type into the optimization problem by breaking up these principal directions into this block matrix structure that represents the flag type. And that's exactly what we do. So now what we're doing is all we did was write U as this block matrix and then separate this optimization problem into these block matrix optimizations. And this will give you something different depending upon, because you're running actually solving a different optimization problem than you were solving to find L2 WPCA. One note with this is there are a lot of different like formulations for robust principal component analysis, and they all have different names, and we tried to use names that somehow make sense to us, even if they're not exactly the names that were given, because there's a lot of like RPCAs out there. There's a lot of robust principal component analysis out there. So yeah. So why would you do this? So one reason that I wanted to do this is that there's sort of this gap between L1 and L2 robust formulations. And of course, you could solve these by just doing like you're just solving minimization problems that are between L1 and L2, where you just sort of encode that into the norm here, rather than going from power of 2 to power of 1. Maybe you could do different powers here. But this is kind of a different way to do it. You're using this representation, right? And essentially you have the L1 formulations, which are things that people have used before normally. These are more robust. Then you have the L2 formulations, which are slightly less robust, but still more robust than normal PCA. And then the flag versions, where you're using sort of a different flag type. And it turns out that like this sort of Stiefel sort of flag type, which is 1, 2, ... to NK, sort of corresponds to this L1. Then the L2 corresponds to NK. And really, I think one way to think about this is what's going on behind the hood is that there's somehow you're just finding a subspace of principal directions here. And here you're finding a subspace of dimension 1 inside a subspace of dimension 1 and 2, and so on and so forth. And so you sort of have an in-between rotational invariance embedded in the objective function here with the flag WPCA. And so flagification kind of fills this gap where you have this sort of in-between rotational invariance. So there are other versions of robust principal directions. So some of them work with an objective function that involves variance of the data. Another one that works with objective functions that involve reconstruction error. And you have various powers of P and Q. And this is a summary table that I took out of our paper. But essentially, I wanted to try to summarize these different algorithms the way that I understood them in one table and how they relate to flags. So the idea is that you can change P and Q here for the norm, and you can either work with variance or reconstruction error, and you can either maximize them or minimize them. So one version so obviously PCA and what I'm calling like orthogonal PCA, which is exactly PCA. Also, all 4 of these squares recover the same set of principal directions, orthogonal PCA and just PCA. If you optimize an objective function with P equals Q equals 2, you recover that. If you start working with Q equal to 1 here, so you remove the square, essentially you have your robust formulations. And now You have the L2 formulations are working with the 2 norm. The L1 formulations are working with the 1 norm. Obviously, you could change between the norms, but we're doing something different. We're using flags to develop new robust variants that are, yeah. And also, right, you can work with what we call like the primal problems, which are finding the subspace that sort of contains your inliers. Or you can work with what some people might call the dual problems, which are you're finding the subspace that contains your outliers in the data. And that's sort of involves maximizing variance and minimizing reconstruction error in the primal problems and in the dual problems. And I'm using dual in like maybe a loose sense. It involves minimizing variance and maximizing reconstruction error. And so all of these problems in black have been done by different researchers. However, there's this one which is like this weird dual formulation, which no one had really thought of yet, it seems. It's the one that minimizes reconstruction error of your data. Maybe this is just a dumb idea, but it should be filled in this table. And I don't know if anyone's really played around with that. So we mention it in our paper, but we don't really do anything with it. It would be interesting to see what this is. So this is you're finding the U's that minimize this objective function for P equals 1 and Q equals 1 or 2. So, okay, flags kind of fill in the gap here, right? Because I'm assigning a flag type to each one of these different types of PCA. And it turns out that, we're missing all sorts of different types of flags. And so we have different optimization problems to fill in these gaps. And sort of how do we go about solving these problems? I'm just giving you a kind of a simple example. So here's one version of, here's sort of the least squares version. Here's the L1 norm version. So you have these optimization problems. Again, no need to look at them too carefully, but you have this optimization problem. There's a square here. There's no square here. You simplify it to a problem over the Stiefel manifold by playing around with sums. And here you can't get rid of the square root, which is a major bummer. And I believe I need another sum here too. But the idea is that you can't get rid of the square root here. And on the left side, we ended up using PyMandop again to approximate the solutions. And on the right-hand side, we did iteratively reweighted versions of the left-hand side. One thing I do want to mention is just last week, it's funny, I looked and there's been some really recent work on this type of problem, which is really interesting. And people have also worked on maximizing the same objective function. There's a lot of cool stuff going on there still. So it seems to be an open area of research for like better solutions and guarantees for problems that look like this. Cool. So just to provide a short example, so we have some inlier images and some outlier images from this UC Merced land use data set, and some inlier images and outlier images from this from where the inliers are pictures of faces from the Yale face database and outliers are pictures from the Caltech 101 data set. And what we do is we just do outlier detection with some of these different variants. And obviously, I mentioned so many different variants of robust principal directions, robust flags of robust principal directions, but we're going to use them to detect outliers. And I mean, it's not, I think with these sort of simple experiments, these algorithms don't really shine. Like the algorithms with the F in front are the flag versions of the algorithms, and the other ones are known versions. These are ROC curves. You have the true positive rate on the left-hand side and false positive rate on the horizontal axis. And yeah, pretty much bigger is better. And I mean, the flag versions do slightly better than standard algorithms. But I think, you kind of have to really be thinking harder about the applications and where we can apply flags, I think. And specifically these types of flagified PCAs to really understand where they're useful. So I also wanted to mention one more thing. In this project, we also were thinking about people running PCA on manifolds. So let's say you had a data set already, you've maybe done this translation. You had data and you know it lives on a certain manifold due to like some constraint sets, due to some physical constraints, or maybe you're working with a set of, I don't know, correlation matrices or something like that, or a set of, yeah, or you have data that lives on a sphere, for example. So now there are these methods for maybe you have inlier and outlier data on this manifold, and there are methods to detect these outliers. So here, this is a silly one where you have data that lives on a sphere, you have some inliers and some outliers, and the top algorithms would be Euclidean algorithms, the bottom would be manifold-based algorithms. And so the Euclidean algorithms, since they wouldn't respect the manifold structure, they give you principal directions just in Euclidean space, and they might be a bad model for your inliers. Whereas if your data is on a manifold and you use directions that respect the manifold structure, so you're actually using tangent vectors to the manifold for your principal directions, then your subspace of principal directions would be geodesics. And in fact, then maybe you could get a better model, especially with the robust formulations on the manifold. And it seemed like not many people had worked with like robust principal component analysis on manifold for manifold value data. I didn't see much work on that, so that was something we were interested in, and then we were interested in taking a flag perspective. But anyways, for PCA on manifolds, the dumbest way to do it is do PCA in the tangent space. All you do is you take your data on this curved space, you compute a mean, and then you map all your data up to the tangent space. So like to a plane that's tangent to your manifold at a point at the mean. You do PCA in the tangent space to get you these directions and you project them back down. There's a lot of problems with this method, and I'd suggest looking at work by Xavier Pennock to understand more about like other versions of PCA that sort of, or PCA on manifolds that solve these problems. But this is the dumbest version, so we wanted to work with this. And so anyways, all these flag ideas translate into this, all the same sort of series of robust formulations translate into this space. So it's really this cool sort of other way to do PCA for manifold value data. And you can also do sort of the flagification and think about robust flagified versions of PCA on these for manifold value data. So it's a really fun direction. So kind of want to conclude here. I realize I moved still a little fast, but better to go too fast than too slow. So as a summary here, I want to talk about our themes. So what I did is I formulated optimization problems with respect to some distances, right? And I translated the problems to be over the Stiefel manifold. And then I sort of found approximate solutions or solutions to these problems using some algorithms over the Stiefel manifold, and then used IRLS iteratively reweighted least squares flavored algorithms to find robust variance. That's kind of what I did in all three of these studies. And we found some utility, some light utility using subspace averages and chordal distance between subspaces to cluster data. We have averages of flags, improve motion averaging. And then flagified robust principal directions improve outlier detection as well. So a little bit more of a summary. We had sort of names of things. We were working on the Grassmann manifold or Grassmannian. We were working on the flag manifold, and we were also working with principal directions. We were doing averages. And so the less robust averages are the chordal GR mean and the chordal flag median or flag mean. The more robust would be the chordal GR median, chordal flag median, and then for less robust principal directions, you can think about flagified principal directions, and for robust, you have robust flagified principal directions. And we have algorithms that correspond to each one of these. You just have like a two-dimensional table here, but for the Grassmannian, for the mean, you use the SVD. For the median, you do iteratively reweighted means. And then for means of flags, you use Stiefel-Riemannian truss regions. For flagified PCA, you use Stiefel conjugate gradient descent. And again, for all these robust variations, you just do reweighted versions of the less robust formulation. So to conclude, I think the world of flags is wonderful. And I think there's a lot more work being done with this stuff than just the few things I've done. And I think the door is wide open for high impact applications to problems in data science with using these types of methods, especially if you want some sort of invariance to rotations or products of rotations. So some of the related works, the first section was talking about subspace averaging, actually was talking about this flag median and flag RLS paper. We use the word flag median and flag RLS because we output a flag, but really we're doing subspace averaging. So that's what this first section was on. The second section where we were averaging flags. This is chordal flag averaging paper. So we're averaging with respect to the chordal distance. And then the last section with robust principal directions on flag manifolds was exactly fun with flags. And then we also mentioned representing hierarchical data sets with flags, and that's a bit of a work in progress, but I'd love to hear if there were any cool ideas for representing hierarchical feature hierarchies with flags and how we can use those there. So some future work, we were playing around with few-shot learning. Maybe there's some physics or causality informed methods I'm interested in playing around with because a lot of people in my lab are interested in that kind of stuff. And I also have other interests like dynamic mode decomposition. I'm also interested in just general dimensionality reduction algorithms and trying to understand how they all fit together, not just principal component analysis. So yeah, I think that's about it. Thank you so much.
Okay, thank you, Nathan. And if you have questions, just type your questions in the Q&A box. And in the meantime, let me ask you several questions.
Hey, please.
So let's start just to be, something very simple, just to be 100% sure, because you talked about flagified PCA, right?
Yes, correct.
Uh, But in the case when you use the L2 error, least squares,
Mhm.
there shouldn't be a difference between the
Ex
two.
Thank you for pointing that out. There isn't. There isn't a difference between the objective function, right?
Right.
And that's I think kind of the point. It's like, well, if you change the space you're optimizing over, you're not actually getting anything new out. And I think there's some works that were doing stuff with this. And yeah, I was really frustrated by it because it didn't seem like there's any difference between these two things. The way to actually get a difference, I think, is this the new paper where they have to think about like a probabilistic PCA approach where they talk about like a generative model for your data based on distributions in the latent space. And then you're also trying to find like a flag type. But I think, yeah, this in fact doesn't change the optimization problem. What you have to do in order to actually change the optimization is actually change the objective function, and then you should get something different.
Okay. So now let's look at what you have below, right? So here, if I don't have a flag, and if I will
Mhm,
first find the first dimensional subspace, second dimensional subspace, third dimension, and so on, they will not be nested
mhm.
when you have the power one instead of power two.
That's correct. That's correct, because
Now,
you have this orthogonal invariance, right? Like if you put in an orthogonal matrix here, it doesn't change anything.
so so then I'm trying to understand, and this is something I missed a little bit in the details. How do you do the flag thing that you get something nested and you still have something that makes sense in terms of the least absolute deviations? Because I don't expect the nesting. here. So I'm not sure what you're really doing here.
So this just outputs a subspace or a flag of type just NK, right? So this part here will just output NK dimensional subspace, right?
Right?
Like as you were saying, like there's not much that's being done here. But when you do something here, then you're sort of breaking the subspace up into pieces.
But they're not nested.
That is a great point. And I think so there's a correspondence between a flag manifold and a product of Grassmannians, right? And so I'm sort of utilizing this correspondence to think about this as a flag. But you're right, you're totally right. You do lose like the like hierarchy, I guess, of the nested sequence of subspaces. You kind of lose like what's the difference between like you should get the same answer if you like permuted the columns here. That's what you're saying, right? Like if you permuted not the columns but these blocks, it's not going to change the objective function, right?
So
So you're right. I guess what I'm saying is that you're right. You're not getting something that's naturally nested.
so it's confused me because you call it a flag, you want it to be nested.
Hmm.
So how does it corresponds to the definition?
Hmm. No, I think that's a fair point. I think what I'm doing is that, yeah, flag corresponds to is not exactly the same, but there's a correspondence between a flag of a certain type and a product of Grassmannians or a product of subspaces. And so what I'm doing is I'm abusing the word flag here and that I'm really talking about a product of subspaces.
I see. Okay, okay, okay.
And then I'm just saying, okay, we're going to use the word flag because there's this correspondence. But I think you're making a really fair point.
So maybe the motivation is you don't have the nested property, and
Hmm.
that's why you introduce this kind of energy that combines all the different subspaces and tries to maybe get something from all of them.
Hmm.
So I see. And you mentioned application, you went very fast. You talked about motion of parameters and you compared with Govindu. This is
Hmm.
for this application, right? For this kind of formulation.
Yeah, so that previous work was with the motion averaging with Govindu, was working with these problems where you're rather than so we kind of had the first part of the talk where I was talking about averaging subspaces and averaging flags. And then
Oh,
I went in and talked about the principal directions. And so this first application with Govindu was talking about averaging um flags actually. So and the way that we did that is you can take a motion and translate it to a flag of a certain type.
but wait, yeah, I understand. Somehow you talked about what work of Govindu you compared with? Because maybe I had something else in mind.
Ah, this is 2001. Let's see. I'm glad I have some of these links actually working. Where are we? Combining two constraints for motion estimation. And this,
And so the goal is what's the error that you're measuring here?
yeah, I think this experiment was done by my collaborator too. So forgive me if I'm not as much of an expert
Okay.
on the results as I should be.
Okay, so
Uh,
yeah, we can communicate about it later. Okay.
I would love to. I would absolutely
Okay.
love to. Yeah.
Okay. So yeah, thank you. Any other questions? Okay, so it seems that we are right in time. Yeah, I'll be happy to follow up with you on these questions later.
That it would be my pleasure. Thank you.
Okay, yeah. Thank you, everyone. Yeah, and have a good night. Yeah, and we'll be in touch. Yeah.
Thanks. Later.
Okay. Bye bye.